Am I still audible by the online participants?
Yes, you are.
Perfect, thank you. Okay, so so I will tell you about the efforts which Flavio has mentioned several times about the parallel I/O in OpenFOAM, especially within it's the parallel I/O effort in the refactoring part of the project. And this is to mention all partners here. So it's led by the HLRS, but certainly we have a very valuable partner in this task, which is Wiki GmbH. They are essentially co-owners of OpenFOAM, and Henrik Rusche is, for instance, he's sort of the idea giver for many things in this task. And Sergey Lesnik is also co-developing. So it's Sergey and me who do the work essentially. Yes, so what will I talk about? First of all, knowing the architecture, I will introduce you a little bit about the parallel file systems and how they look like in HPC systems, just to give you a brief update or get everybody on the same page. So then the file system, also libraries. I will give you one example of a library which we will in the end which we use, and a data access pattern, why they are important. Then of course introducing you to I/O formats or how OpenFOAM is doing this right now, and then finally go into the details what we did with OpenFOAM to make it or its I/O to make it parallel, using the Adios transport layer, exactly that library I just anticipated. And then one very important part is a new mesh comprehension, a so-called, we call it the coherent mesh comprehension, which addresses the data layout, the access pattern. And we also have some results, benchmarks, even on larger scales now. I will show you all of this today. Yeah, so in general, parallel file systems, they do something for you which is beneficial for you. Of course, it gives you bandwidth because it stripes your file into several sections and puts it onto several targets. Thus, you get the aggregated bandwidth of all these targets, like really the sum of it in theory. That's the first bullet point, let's say, and this is this picture, but then the next picture is abstraction of the file system and how it kind of is interpreted in many of the existing parallel file systems. You have inodes, which are sort of your index cards to a bigger archive of your data. And this archive is stored on your targets, so the disks on the very right side. But in between, you have your lookup servers, which handle these inodes. They are requested by the compute nodes to give out some data or to store some data. And these requests, they are worked to these servers, to these lookup servers. So overall, it's always the target. Actually, the last bullet point, lookup suffers contention if overutilized by many requests, to minimize the number of requests. And all other things which are written on the slide are basically the same or come out of this consequence. So let's say keeping the number of files small is one consequence to keep your requests small. Or having less I/O operations means less requests. Having larger access size, so optimize access size for big sizes, that's also towards the target of having less requests to the file system. And also, just to put this into perspective, this is a shared resource, so if there's something contention happening, then you have to, other users also have to deal with that. Okay, and then of course you don't have to do everything for yourself in your application, and there are libraries, and one of them is Adios 2, and Adios 2 is essentially the only one I will introduce you for today. It's the one which we use in this project. It deals with this N by M model, which means you have N processors and M files, and so M being smaller than N, and this model is yeah, it's the in-between case of two other, you can also have the limited case of N by 1 model or the N by N model, and the N by N model is certainly not the one you want to choose on parallel file systems. It's the one which generates a lot of requests. That's why you have this intermediate model where you scale down the number of files, and these ranks might be aggregating or they are aggregating your data into these subfiles. Okay, and Adios does this in a way that it has these binary files where it stores all the hard data. You can choose the number of files flexibly at runtime. Also, even with the newest file format, the BP5 format, you can choose a different number of files than the aggregators. That is also a new feature. You have features like asynchronous writing, which you can exploit given your implementation. But Adios, or it's not too big of a but, let's say, it requires a contiguous access pattern. What do I mean by that? It's essentially there are other I/O libraries which also allow an irregular access pattern, but Adios prefers and does so in a contiguous access pattern. The data from one process has to be as a sliceable chunk, so you only have a start and size to where the data resides in the file. The irregular access pattern does some extra mapping work, exactly this kind of very irregular work, which certainly will generate some sort of overhead. And it's better to have the control over this overhead in your application than giving it off to some library. So make it simple, essentially. Okay, then let's dive into OpenFOAM and how OpenFOAM does its I/O right now. We have the uncollated format, which is this N by N model, which is what I mentioned earlier. It is essentially a showstopper at scale, because then you will have as many inodes or as many files as processes, and that at some limit, there's always a limit with coupled to your user account. For instance, you have a quota limit, and for instance, that you will hit before you even might be penalizing also the full file system and other users. But more importantly about the uncollated format, and also about the collated format, which I will come to on the next slide, is you have to decompose your case, you have to reconstruct it or potentially redistribute it. You have a lot of tools which handle your mesh for parallelization, and it will then subdivide these mesh parts into these processor folders. And yeah, okay, about the data structure, I will come to that a little bit later, but yeah, these tools are also very costly in the time to solution. And also as an engineer, you might be, you want to change something small in an ASCII file, like a boundary condition. And in that case, for instance, you will have to go all your processor folders if your case is decomposed on a large cluster, then this is tedious work. So you might be able to save that. And one way to do it, to already deal with this showstopper of inodes, is using the collated format, which exactly introduces this N by M model. It reduces these number of inodes. but the mesh comprehension is still the same, the whole mesh layout. It just basically collates, as the name does. It just glues together all the information from a certain subset of ranks. So let's say you have a decomposition on 512 MPI processes, and you might aggregate all the data of the first 128 ranks into this first folder and so on. Okay, so the time to solution penalty is still there. And this is also somewhat anticipation here. I have some benchmarks later on, and you will see that at scale for a large case, this time to solution, only the pre-processing can take days. So what is it, what I'm talking about, the mesh layout, mesh comprehension? How does the OpenFOAM mesh look like? It's the mesh connectivity stored in terms of owner and neighbor lists. So faces, it's always a face ordered list. You will always have the internal cells being numbered first. Sorry, internal faces, they are the first, the enumeration follows the internal faces first, and then the boundary faces are attached at the end of your owner list. Thus, the neighbor list, there are no neighbors to boundary faces, is shorter. Then once you decompose such a case, everything is renumbered, re-enumerated on your particular partition. And actually things get new numbers, new addressings, because they have to start from 0. So there's not a global enumeration anymore, or there is, but you explicitly store it. And locally, you have your local enumeration starting from 0. So it's a lot of back and forth renumbering that is explicitly stored, fragments the whole mesh. So this data layout pattern is somewhat, it could anticipate to have a irregular IO access pattern. Okay, so how do we solve this? First of all, yeah, okay, no, sorry, not for, first of all, let's go step by step. So just to summarize, our objective for OpenFOAM was get rid of the showstopper for inodes and also reduce the time to solution by a new data layout or IO access pattern, which gets rid of many of the pre-processing work that has to be done. The approach was exactly, as I mentioned, the ADIOS 2 library to integrate that transport layer into the core of OpenFOAM. So the core libraries are really refactored. This is refactoring work inside OpenFOAM. And then design this new mesh layout, which we call the coherent data access or layout access pattern. Yeah. So the transport layer, this is very technical. I will just skim through this. This is how we have had to do it inside OpenFOAM. It's the IO is very serial. So you go through all your classes and they will have friend operators to these extraction or insertion operators, and the underlying stream is passed to all of your functionality and collects your output line by line. So it's a very serial design. But for a parallel IO, you might want to gather, collect information about where the data resides, what the amount of data coming from a rank. Also, we have identifiers like this is a velocity field, this is a pressure field, and so on. So putting everything in a more deferred way, in a more deferred IO, we redesigned that for the ADIOS inside the libfoam, the core library of OpenFOAM. Okay, then given that, and having this transport layer installed, essentially, we now can think of the new mesh layout. And this new mesh layout, it's essentially the connectivity and the whole understanding of the mesh is still the same. We still have connectivity of the mesh by owner and neighbor lists, but we impose a more strict upper triangular ordering or some more rules on the mesh layout. So it's a stricter comprehension of the mesh. First of all, we order our faces by ownership. And this way we can design, or we can now store instead of a face ordered owner list of cell IDs, we can store a cell ordered list of face IDs, which is called the owner start list, but it's essentially so then you will learn from this cell, from this list, you will learn that your first cell or your 0th cell starts with the 0th face, of course, and then the first cell or cell number 1 starts with phase 4. So you're iterating through phase offsets. And that introduces one more layer or one more layer of your dimensionality. Now you can go through your dimensionalities like 3D, 2D, and 1D. In case of OpenFOAM, we don't have edges. And those are coherently connected. So this format is now sliceable for within one of these lists, but it's coherently connected. So there's logic behind these dimensionalities. Okay, in fact, you go to this cell ordered list and you read off its value, and you know exactly which where to slice the face ordered list. And from the content of the face ordered list, you know where to slice your point ordered lists. Okay, yeah, so exactly. So when you would now partition this, you can actually keep a global view. So you have a global enumeration, and you can now also transport some information which was explicitly stored before, like processor patch boundaries. You can transport that through communication to the partitions which need it. Going away from these numbers, I actually also didn't go into much of the numbers. It's also one particular example, but the comprehension now is sort of a tree structure. You can think of a tree of it. So it has a coherence through your dimensionality layers, as I said, like cell ordered, face ordered, and point ordered objects. Now this can also be fields if you wish. It's a point field or face field. You can understand this connecting it to this tree structure. So you see, for instance, here the neighbor and faces, they are both face ordered lists. They connect to the upper level of your cell ordered list, the owner starts, and so on. And then you have, through this coherent understanding, you have a sliceability. You know which chunk of which list goes on which partition. If I read this chunk of cells, I need this chunk of faces, I need this chunk of points, and so on. Okay, and this is also, of course, transported, as I said, to the field I/O. The field I/O adopts this coherence from the mesh, as it always has done. It adopts the data structure from the mesh, whether it's the polyhedral, classical polyhedral mesh, or now this new comprehension of it. We have a little bit of a differentiation here. I didn't actually say that regarding the mesh structure. But here explicitly we separate boundary and internal fields as you know it, just to also store more complex boundary patch conditions. Yes. And then there's that's something important to mention. It's we do more work because we're moving some of the work which was explicitly, or some of the information which was explicitly stored in addressing, etc., or maybe even double storage of information on one processor and on the other processor. Now we do extra work, slicing off, for instance, in our surface fields, the processor patch information. We have to put this into the internal surface field, and so there's reordering, reshuffling work, conversion work, essentially. Yeah. We have two layouts currently working and also playing with. This is very recent and experimental. Let's say we certainly support one format, which now looks like this. So this is actually the interesting news for any OpenFOAM user. How does your case look like? You don't have processor folders anymore. They are totally gone. You only have time directories left. And so essentially your case looks like it is a serial case. Okay. We store ASCII information. We still store that. You need some information that how you specify your boundary condition, etc. We still store that inside field files like U and P and Phi. But the hardcore data really goes into these data.bp files, whereas we have two modes. We have a mode which is the time folder or time. Just for the sake of this talk, this is not like this is how you will use it later on, maybe, but a time coherent mode, let's say. It makes it very easy to run several time steps, do the IO, and then throw it away. Okay, but if you know more precisely what you actually want to store, you can also use something like a case coherent format where you store this hardcore data, the biggest amount of your data, inside a data.bp file, which is located in your case folder. And that is something which we did for performance reasons. Opening, closing a file is then spared, essentially, and yeah, we can see some benefits also on the next slide. Yeah, again, handling fields just like a serial case, and that's really interesting information for the user. Other very interesting information for the user is presented here on this slide. So it's really results from what we are measuring right now, benchmarks that we conduct. Let me go into this a little bit in detail. So let's focus on the first figure up here. So we have our pre-processing, the timings of our pre-processing. I'm thinking of a weak scaling case. I want to take the case and increase its size for now. It's a 3D cavity case. In the end, IO just deals with velocity and pressure fields. I don't care too much about whether it's the cavity velocity or some other case. But okay, let's say we take the cavity with 1 million cells. That's, for our system, it's roughly the sweet spot of having 1 million cells on one node. It refers to 8,000 cells per core. That's somewhat the performance sweet spot, which we have learned also in the Exaform project. And then taking 2 million cells, 4 million cells, and so on, it translates to the number of nodes which you could use in a weak scaling study. So now, what I'm pre-processing these cases of different sizes in the collated and now the new coherent format. So I'm using block mesh and decomposed par. This is a logarithmic scale. This is important to mention because essentially the very first part of one bar is the block mesh contribution, which is, for instance, up here we have a 500 million cell case. this is 50 minutes of block mesh, and then 45 minutes, so roughly the same amount of decomposition. Okay. With the collated format, I cannot even do this within the limit of our queue. We have a limit for a job to run, it has to be finished within 24 hours, and that is the red line. So I can do this workflow up to 128 million cells. And then there's a hard wall essentially for our system. Of course, you can now start thinking of tricks, maybe start with a smaller mesh, refine it, etc. But this is, again, this is work which the engineer has to think of, where time goes by and passes by before you actually have your solution. Okay, just sticking to the same workflow, we see that with the coherent format, we really reach now case scales and also scales of your system when we translate this to the number of nodes again, that wouldn't be reachable with a collated format. And that is not just because we accelerated things. So we spare some work, some of the work of the explicit addressing, for instance, which has to be stored in the collated format, but it's really a time complexity improvement. So the coherent format this is a linear scaling, essentially, and for the collated, we have n squared. And that's why we save so much time. And then extrapolating, you can also extrapolate it and say, okay, we actually saved, this is a week up here, right? The gray line. So days to minutes to hours, let's say. Actually, another side effect of the whole coherent mesh is you don't have to decompose it anymore. You actually can, once you have your block mesh within 50 minutes, you can actually just start a parallel run on it. And that's also one of the benefits. You don't have to redistribute. You don't have to decompose if you want to run on a different number of cores again. So we have a major gain in the time to solution. In the time of the I/O during your actual simulation, we are on par with the collated format, and that's the plot down here. So this is now the run. This is I'm going away from the weak scaling that I just mentioned. This is now strong scaling. I'm taking this case up here, which is 64 million cells, and I run it on different number of nodes. So a strong scaling study. I'm seeing an efficiency which is decent for all formats. I'm comparing here this, of course, the collated in green, and then this time and case coherent, though, whether you store your hard data inside the time folders or in the case folder. In the case folder, as I said, you can keep the file open a little bit longer, so you improve a little bit the scalability down here over the time coherent, but overall, all formats are on par, essentially, so you don't have big losses or big gains. Okay. Yes, so many of the benefits I already mentioned. It's you don't have to, you can just start the parallel run without decomposition, or you can also choose to run on a different number of cores once you have your pre-processing done. Also, the no reconstruction for post-processing. So also returning to this plot, this is the workflow for collated is not finished. After the pre-processing, you will certainly have to reconstruct. With the coherent format, you don't have to do anything anymore. You can start analyzing your data. Yes, and the case handling is just a very serial feeling. Also, this includes, of course, the first two bullet points. but also other things like what I mentioned, when you want to change something in your boundary condition and you ask information, you just go into your time folder and do it and don't have to script things or something. Yes, and that's also why we recently achieved this very large run. So this is one of the largest run to our knowledge. So we, like, powered by the coherent file format, now we were able to run up to 2048 Hawk nodes, which refers to more than 260,000 cores. Yeah, so if you want to follow this in the Exaform project or the HLRS channel, there will be more actually to come, because there's at least one more level higher. Yes, with that, let me conclude. Yeah, I mentioned all of this. It's we have this new parallel I/O format. It's not just implementing a new transport layer. It's really it's a new transport layer in the OpenFOAM, so really refactoring the core library, but then also introducing a new mesh comprehension, new coherent mesh layout, and it significantly simplifies your user experience and also the time to solution, vice versa. But more interesting to mention here still is, so this will go into production code, of course. So we are, so the partner from Wiki GmbH, they are involved in the foam extent development and code owner of that. So it will certainly go into that. And also other versions are, we are talking with the work package 6 essentially, which is for porting of and exploiting the outcomes that we did. The last bullet point, let me just mention this also. It's there are other features now which somehow anticipate from the new file layout. So as I mentioned, you might not have to decompose anymore, but you can now also impose a decomposition during the startup phase of your run. So this is a feature which still would be have to be implemented in future work. Dynamic load balancing can profit from that. Also, you can selecting a subset of cells means you can analyze regions of interest in your case much easier. And also the asynchronous I/O feature, for instance, from Adios, is something that we can also still exploit. Thank you.